Hello everyone. Today we are talking about Newton's third law. So this is the law of action and reaction, or the law of forces in pairs. So this law is really interesting. One of the best examples of this law is the idea that of swimming. So when you push water away with your hands when you're swimming, why do you move forward? That's sort of a question to think about. So when we're in the pool and our hand is, hands are always hard to draw here. Okay, so this is my hand in the pool, and it's moving. I'm actually pushing on the water, right? This is my water here. I'm pushing on the water with my hand in the reverse direction, but for some reason, my body starts moving forward, and my body is accelerating in the forward direction. We said acceleration is a sign of force. So what this means is that when you apply a force in one direction, you also receive an equal and opposite force in the opposite direction. So this law is generally stated as for every action there is an equal and opposite reaction. So for every action here means force, there is an equal and opposite reaction. So another way of thinking about it is in terms of action is we might also think about acceleration. For every acceleration, there's an equal and opposite acceleration. We could also say every force, there is an equal force that opposes it, or that all forces appear in pairs. So think about this right now. If you're sitting in a chair, for example, then the chair is under the force of gravity. So there is a pull down on the chair from gravity, but the chair does not collide with the ground, so there must be an equal and opposite force holding the chair up, stopping it from collapse. Because if we took away any one of these legs, the chair would fall over. And so that is the reason the chair stays in place, is the chair is getting a force. The force is coming from, this force comes from all of these legs, but all of those legs also put a force down on the ground. So everything is in a pair. The force that initiates the reaction is called the action force, and the force that responds to the initial action is called the reaction force. So these are the terminology we're going to use, is there's an action force and a reaction force. And we're going to try to talk about some of the times where things are changing and moving to have that discussion. So one of the biggest misunderstandings people have is they mix up the action force, which results with the results of the paired force. They fail to understand what exactly the reaction force is. Okay, so this is one of the problems, is that we'll realize after adding up the action and the reaction force, that's when we get our net force, which is the force that we actually experience. So even when we talk about this, when we go back to this movement example where we're swimming, in the case of swimming, your body is exerting a force here, and the water is going to respond. But then when we have to add in a couple of other forces like drag and friction, and then the body moving through the water. It's not a direct. You don't get a direct experience. The stronger you push in the water, sure, you do go a little bit faster, but there are other forces involved as well. But it's not just the net force. Your body initially exerts a certain amount of force on the water, and then we add in a bunch of other, and the water exerts a certain amount of force back, and then we get a bunch of other forces that oppose it till we get the net force that causes the body to accelerate through the water. Okay. So let's consider this. When you walk, you push backwards on the ground, right? So when I'm walking around, what I'm actually doing is I'm lowering my foot touches the ground, and then it kicks backwards, pushes backwards on the ground. And so to go faster, what I'm actually doing is I'm applying force backwards to go forward faster. If you're on a wheeled transport of some sort, the wheels push backwards on the ground, And so Newton's first law says that you will accelerate more if more force is applied.
Where do you go?
Here. The more mass something has, the more force is needed to accelerate. So this is from the second law, right? So the first law says that you will accelerate more if more force is applied. The second law says that the more mass something has, the more force is needed to accelerate it. So when we combine those two things, this is where we start to realize why we're moving at all, etc. So for example, here this woman is taking a walk, and so she is applying a force backwards on the ground, and then the ground and its friction is applying a force forwards as well. That allows her to move. When these wheels are moving, these wheels are actually, they're pushing down on the ground backwards, and then the effect is that the reaction is a forward force, which is eventually what's going to cause the wheel to turn, or the overall action forward. So why do you go faster when you push backwards harder? Well, this is from third law. If you push backwards on the ground pushes forward on you with an equal force. But you and the earth are different masses, right? So this force here being applied to the earth in this push-up, well, this is a little tiny bit of force, right? This is a certain amount of force, and it's force related to the mass of the earth, and will give us some acceleration. If you are thinking mathematically, that's going to be a very small number, because this force is the same as this force. And this force is now going to be the mass of u, and that's going to be times an acceleration. And certainly the acceleration of u compared to the acceleration of the earth is going to be much more. So when we push down on the earth is so massive, it doesn't really change, it doesn't really accelerate, it doesn't move anywhere. There's a thought experiment that we can work out, we might work that out in a physics 30 class, is what if every single person on Earth tried to jump at the same time from the same position? Would that be enough mass that we could exert enough force to actually move the Earth? And I believe someone worked out the math on that. I'll let you think about that one. The answer is no. Okay, so you move forward because the amount of force you apply to the ground, i.e. the whole planet, is not enough to accelerate it backwards very much. However, you have a very small mass compared to the Earth, so you get a much greater acceleration forward. If you push harder backwards, the Earth pushes forward equally hard, and you'll accelerate. Yeah, and we'll use an example in a second. So to use the terms of the third law, the action force is you pushing on the earth. So this is for running, right? This is still running. We're still talking about running. So the action force is you pushing on the earth. The reaction force is earth pushing on you. The result of this pair of forces is that you observe is that you are accelerated in the direction the earth pushes on you, much more than the earth is accelerated in the direction you pushed it. So we have this massive planet, right? And then there's a little tiny u at the top. This is what everybody looks like when they run, right? I think maybe if I fix this hand. Okay. And then at the top of the earth, you are going to be kicking that foot backwards, and the earth is going to give you the opposite response. And these are equal and opposite forces, but the mass of the earth is this massive earth, right? So this is going to be your force, and it's equal to this massive earth value. times a little tiny acceleration. And then over here, this is the Earth's effect, right? This is the force of the action. This is the force of the reaction. And it's equal to your mass, u, times acceleration. The same acceleration should be the same. Or it should be different accelerations. And different accelerations to give the same force. So the forces are equal, but the masses are not. So if the forces are equal, but the masses are not, then the accelerations are not equal. So forces are equal, but not the masses being acted upon. Now this is where collisions become really interesting. We'll talk about momentum and the conservation of momentum in a second. By a second, I mean the next video. Because something like billiards, where you have billiard balls, pool balls, those are two masses that are equal. So when the two masses that are equal come into contact with each other, they often, the action-reaction pair, are equal. So they'll have equal action. And there's a lot of interesting things you can do with that. So here's some example. So if you want to open a door, maybe this guy obviously is working hard on opening a door that is closed. And I feel like this door, if it's a door, it should have little door handles or whatever. So when he's pushing on the door, he pushes on the door. This is the action force action on the door. And the reaction is the door pushes on him. And if it's a really sticky door, then he'll actually be able to feel that reaction force against him. And he might not even move, right? When the lock is in place, then the door doesn't open. And so in that case, as much force as he applies, that door is probably going to stay in place. And if you, maybe if it's a really stuck door, he might actually have to apply an amazing amount of force. He might have to actually kick the door open. And in that case, he might even feel that reaction force on his foot as he kicks it in. Now, in this case, the door is likely to not as strong or not as massive as the person, and so the person should be able to apply enough force to move that door. So you feel the resistance as you push. The heavier the door, the more resistance you feel. The result of the pair of forces is the door moves away from you. Okay, down here I have two examples that I've kind of drawn out. One of them is a soccer ball and a person kicking the soccer ball, and the other one is a bowling ball and a person kicking the bowling ball. So let's think about the soccer ball first. So when you kick a soccer ball or a football, if that's the language you like to use, then the ball gives a reaction force on the foot. And if you kick a soccer ball incorrectly, you might notice that that feeling of the force. So here, I'm going to kick this is my soccer ball, and this is my force here. And maybe I'm going to go with a smaller force for this one. Okay, so here's my force for my foot, and here's the force the ball exerts on me. So this is my action force, because my foot is the one that's moving and initiating that contact, and then the ball gives that reaction force against my foot. And if you try to kick a soccer ball without shoes on, you'll notice that there's a little bit of sting left in your foot if you stub it wrong. And in that case, the soccer balls have some mass to them, but they maybe even have a mass that compares to your foot. Now, kicking a bowling ball, on the other hand, this is a case where you'll have to be very careful about kicking the ball because the bowling ball is much more massive than the soccer ball. So you can exert a lot of force on this bowling ball, and it might still not accelerate very much. So to make it move, you're going to have to kick it very hard. So we're going to have that initial action-reaction pair. Here's the force of the action from your foot, And in fact, in this case, I think we could even draw it out as being a more massive force, because you can kick very hard on this ball without seeing it move very much. The mass of the ball is much higher. And then that means that there is an equal and opposite reaction. So actually what you should be doing is even measuring out how long an arrow you drew so that the arrows are the same, because they're equal and opposite. Now this larger force, right? You have a force of action. You're taking a really big swing to try to get this bowling ball to move. It has a lot of mass, so it can exert a lot of force. And so it needs a lot of force exerted on it to make it move. That means that your toe is undergoing the same amount of force in response. So the reaction force is also very large. And you could break your toes, right? You could break your toes by under that force of that reaction. And so that's the action-reaction pair. And I will post you a little link to some videos and some questions about that in the next day or so. And with that, have a great day, and we will come back and talk about momentum in our next video. Bye-bye.